Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello. This problem seems rather difficult, but it actually requires thinking back about our ideas of torque and statics problems back from Physics 1, and thinking about applying force diagrams and Newton's laws for rotation to figure out the angle at which this current carrying metal rod is being suspended in this uniform magnetic field. So just getting a quick overview of what's happening here, we draw our picture. We have a region of space where the magnetic field is headed into the screen everywhere. We have this metal current carrying rod that is at rest at an angle theta from the horizontal. And again, we have a current I going through this rod. Now, if there's a current going through the rod and it's in an external magnetic field, there will be a magnetic force. So really what's happening here is we have the magnetic force, the gravitational force, and the hinge forces all balancing out here so that the object stays at rest, and we have all the torques that are being applied from the magnetic field and gravity that are also balancing so that this thing remains at rest and not rotating. So how do we figure out how these torques balance? Well, the main thing we're going to do is draw a force diagram and think about what forces are acting on the rod and where and in what directions. So let's draw a force diagram of our rod. So our rod is on a hinge at point P at the end. The rod goes up and to the right like this, like so. And let's think about the forces that are acting on it and where and in what directions. That matters a lot. So one thing that we often forget about but are very important in problems like this are the hinge forces. So we're going to have a force from our hinge acting up at this end. I'll call it the hinge force in the y direction because I'll define my upward as positive y and to the right here as positive x. Then I'm also going to have a hinge force acting to the right here as well. Next, we have gravity. And which way does gravity act? Well, gravity acts straight down towards the ground and acts at the center of mass of our object. The center of mass of the object, since it's a uniform metal rod, is going to be at the center of the rod, and the gravitational force acts straight down. And we'll represent that gravitational force, of course, as the mass of our object times the acceleration due to gravity. Now, the next question is, what is the direction of the magnetic force acting on this object? Well, remember, we have our current, we'll kind of use our diagram over to the left here, we have our current heading up and to the right, and our magnetic field heading inward. So if we do our right-hand rule, we put our pointer finger along the direction of the current, so this way, and then we rotate our wrist so that our middle finger is pointing down into the screen, like that. When we do that, we see that our thumb actually points up and to the left. So that is the direction of the magnetic force. Let me rewrite that word. A-G. So the magnetic force is up and to the left like this. So when I represent that on my force diagram, I'm going to draw it perpendicular to my rod, up and to the left. So that is the direction of the magnetic force acting on my object. And I know that the magnitude of that magnetic force is going to be given by my equation for the force on a current carrying wire in a magnetic field. IB, or ILB sine. In this case, I'll use phi because it might be different than the theta that we have in our diagram here. The angle between the current direction and the direction of the external magnetic field. Now, let's actually think about that real quick. What is this angle phi? What is the angle between the current carrying direction, which in this case is up and to the right, and the direction of the magnetic field, which is into the page. If we think about that, these two are perpendicular to each other. So this phi angle is actually 90 degrees. And again, sine of 90 degrees is going to go to 1. So in the end, we have a magnetic force acting up and to the left on a rod, perpendicular to the rod, of magnitude ILB. Cool. Now what we want to do is figure out how the torques balance. Now, if we think back to how we figure out a torque, what really matters is we figure out where the force is acting, so we call it a distance r, from a pivot point we define to the point of application of the force, multiplied by the part of the force that is perpendicular to that distance r. So, if we wanted to figure out the torque due to gravity, we first need to figure out where the gravitational force is acting from a particular pivot point. Now, forces that act at the pivot point create no torques because the distance from the pivot point to the point of application of the force would be 0 because we've placed our pivot point at the point of application of the force. That happens if we put our pivot point at point P. What happens if we put our pivot point at point P is that we have no torques being applied to our rod due to the hinge forces. So there's going to be no hinge force torques, and the only torques we have to care about are torques arising from the magnetic force and the gravitational force. So for our gravitational force, we get back to that. Where is that being applied on our rod compared to our pivot point? Well, it's at a distance of 1/2 of the length. Oh, let me change back to black marker here. It's 1/2 the length of the rod. That's where the gravitational force is being applied. But now we want to find the component of this downward gravitational force that is perpendicular to that distance r that we've measured. Well, if you remember about forces on inclines, the component of gravity that is applied perpendicular to this rod is going to be mg, so the magnitude of the gravitational force, multiplied by cosine of theta, which is the theta we want to find, right? It's the theta at which this rod is being tilted from the horizontal. So the torque being caused by gravity is 1/2 this length of the rod, because that's where the force is being applied as measured from our pivot point, and the part of the gravitational force that is perpendicular to this distance 1/2 L is mg cosine theta. So that is the torque being applied on the rod from gravity. And that's going to try to make our rod rotate counterclockwise, right? Clockwise. So the rod would want to fall, and we're going to rotate it clockwise. Because it's going clockwise here, this actually is defined as a negative torque. So we have the gravity is trying to make this thing rotate clockwise, therefore is causing it a negative torque on this object. Now, because there's no torques from our hinge forces, the only other force to consider besides gravity is the force from the magnetic field. So what is the torque acting from the magnetic force? Well, the problem tells us we can consider the magnetic force acting at the center of gravity, and therefore it's acting at the same place as our magnetic force. And I've actually reflected that in our force diagram already. So if we write out the distance that our magnetic force is acting on, it's the same. It's 1/2 the length. But then we have to find the part of the force that is perpendicular to the rod. Well, if we look at our diagram, the entire magnitude of this force is the entire force itself is perpendicular to the rod, and therefore all of this ILB is contributing to the force that causes the torque from the magnetic force. So I just have to write ILB here for the entire part of the force that is perpendicular to the rod, because all of the magnetic force is perpendicular to the rod, right? I could draw a little thing here. Okay, so because this object is not accelerating or changing the way it rotates, that means the net torque acting on this system must be 0. So all of the torques acting on this must add up to be 0, and therefore the positive torque from the magnetic force, because this force is trying to make this thing rotate counterclockwise, the positive L over 2 ILB added together with the negative 1/2 L mg cosine theta must add up to be 0. because the two torques from these two forces must balance out. So when I solve for this, what I see is that these two just equate to each other. Let me section off myself a little room here. So we have these two must be equal to each other, and what we'll see is that the L over 2's actually cancel out. They actually cancel out over here. So what we have is a balance between ILB and mg cosine theta. So a balance between the magnetic force and this particular component of the gravitational force. Now, what we're interested, remember, is the angle that this rod makes with the horizontal. So I'm going to solve for cosine theta and then take the inverse cosine after. So cosine theta is equal to ILB divided by the mass times gravity. Now, if they plug those things in, what do I have? Well, the current being carried throughout this wire is, sorry, 1 second, my screen went to sleep. Let's see. Okay, let me write these in now. So the current is 4.1 amps. The length of this rod is 0.45 meters. The magnetic field is 0.36 teslas. And we're going to divide that all by the mass of this rod, 0.094 kilograms. And we're going to then multiply that by 9.81 meters per second squared. Now, in the end, we'll plug this in our calculator and then take the inverse cosine of that value. So if we take the inverse cosine of all of this, and I'll let you guys plug that into your calculator, we'll see that we get an answer of 44 degrees. And that is how far this rod is going to be hovering, what angle it's going to make with the horizontal, because of the balance of the magnetic forces, the torque caused by the magnetic force, and the torque caused by the gravitational force.